So now let's continue with the mathematical model. So now we have already calculated the useful heat gain from this fin to this tube area and from both sides of the fin. But actually the useful heat gain to this fluid is not only from these two fins, but also some of the energy is directly absorbed within this area, which is not the fin area. This area, which is, or this part of the absorber plate, which is directly above this tube, it is also absorbing the same solar radiation, and the energy is being lost from this area also. So now we have already estimated the heat which is conducted through this fin from this side and also from this side, but there will be energy which is absorbed directly over this tube, means this portion which is starting from here till here, right? So this portion of the absorber plate which is directly over this tube is also absorbing heat. So that's why useful gain of this solar collector also includes the energy which is collected exactly above this tube region, and that is given here. And above this tube, if we see from the top, it is like this one. If I draw the top view of this portion, so it is like a rectangular portion which is exactly over this tube, which has this length which is equal to the outer diameter of this pipe or tube, and it is the same length L of this absorber sheet. So this area D into L is the area which is also absorbing heat. So on this side this is fin, and on this side this is also fin. So we have already calculated this heat transfer through the fin reaching in this area, but this area is also absorbing heat directly. So this heat which is absorbed in this area, which is D into L, is given by this equation. So here for this area we can write the same energy balance, but the area is actually D into L into S for this area, this energy absorbed in this area, minus UL into TB, and we already said that this at this base of this fin the temperature is TB, and this TB temperature is for this whole portion. So it means this whole portion of the absorber sheet, which is exactly over this tube, is at temperature of base temperature of TB. So from this base temperature till ambient, the loss is given by UL, overall heat loss coefficient, again from the top and from the bottom and from the edges. So UL into TB minus T. So this is the heat transfer or the net heat absorbed by this portion having an area of D into L, right? So this is called the heat transfer in the tube area. So for per unit length, this is small q dash tube. Per unit length means L is equal to 1. So that is equation 4.29. So the total heat which is absorbed is actually the heat which is absorbed from these two sides of the fin plus the heat absorbed over this tube area. So the useful energy gain per unit length in the direction of the tube flow, in the fluid flow, is given by the heat which is coming from the fin plus the heat which is absorbed exactly over this tube. And this Q fin, which we have already derived in the previous slides, and this Q fin coming from this side and also from this side, per unit length L is assumed 1 is given by this equation, where this portion, this part or this term is actually represents the fin efficiency. So the total heat which is gained in this portion, in this entire region, is the heat gain from the fin portion plus the heat gain from directly over this tube. So the summation of these two, Q fin plus Q tube, is the total heat gain of this absorber plate. So just sum these two terms and represent this term tan hyperbolic of m into w minus t divided by 2 over m into w minus t divided by 2 as f, the fin efficiency. Right, so then add these two. So after adding, this is the final correlation of useful heat gain per unit length, because it is represented by small q with prime, so it is heat gain per unit length of this absorber plate. So after adding these two and after little adjustment, so this is the final equation. So the total heat gain for the whole length is now given as d into L, so Q of tube plus Q of fin. So this tube portion plus fin portion is added for the whole length, and in the next step what is done here, this portion s minus u, this part s minus u into tb minus dA is common in both of these terms, so that is taken out, right? And L is also common in both of these terms, that is also written separately. So inside what is left, d plus f into w minus d, right? So that is the same equation which is written here. In the book everything is written for per unit length, but for better understanding I am keeping this length L shown here. This is the total length L of this absorber plate. If you see this absorber from the top side, from the top view, that is the top view of this absorber and tube portion which is shown here. So that is the useful heat gain at the top of this absorber, right? So let's continue further, because we still want to get rid of this base temperature, because that is an temperature which is not known to us. So we want to get rid of this base temperature, and we want to shift fluid temperature, because fluid is flowing in this pipe at certain temperature. So now we want to have an equation of the useful heat gain of the solar collector in terms of fluid temperature. Okay, so now whatever heat which has been absorbed over this tube portion, it means on this absorber plate, will now be transferred to the fluid. So the total heat which is absorbed over this tube in this absorber sheet is given by this equation 6, right? So this energy, this QU, this useful heat gain of must be transferred to this fluid which is flowing. And now from this sheet, from this absorber sheet till this fluid, there are further thermal resistances. First of all, there is thermal resistance due to this welded bond between the absorber sheet and this fluid pipe, right? And also there will be another thermal resistance due to this conductive resistance due to this pipe thickness. This pipe has certain thickness, so that represents another thermal resistance between absorber plate and the fluid. So normally this pipe or tube is made up of very highly conductive material like copper or steel, so or aluminium. So, and also the thickness of this pipe is so small, so we can easily neglect the thermal resistance of this pipe material itself. So here we shall consider the thermal resistance of this welded bond and the thermal resistance of this the convective thermal resistance of this fluid, which is given by HF 1 over HF into the area, right? So this energy Q, which is given by this equation 6, which represents the heat, which is net heat which is absorbed by this absorber sheet, from the fin portion and plus from this portion will now be transferred to the fluid. So between this absorber sheet and the fluid, now there are two major thermal resistances, one due to this welded bond, and second due to the convective heat transfer resistance of this fluid which is flowing through this pipe at a certain mass flow rate. Right, so now we can write the same Q which will now be transferred to this fluid has to encounter these two thermal resistances. So from this point, at this point temperature is TB, and inside this pipe fluid temperature is TF. This local fluid temperature is given as TF. So this is the temperature difference, TB minus TF, and due to this temperature difference, heat will now be the same heat which was gained by the absorber sheet will be transferred to this fluid. So here is the heat transfer of this heat transfer to the fluid part is given as TB minus TF, and between this TB and TF, these are the two major thermal resistances due to convective heat transfer resistance of the fluid flow and the bond conductance, or 1 over Cb represents the heat transfer resistance due to this welded bond. So here now let's try to understand what is meant by this the bond conductance due to this welded bond, because from this TB till TF between this absorber sheet and the pipe there is this welded bond. So this welded bond, now heat transfer is in this particular direction, right? So in this direction this bond is made up of some solid material, and that's why the heat transfer through this welded bond is by conduction. So we can write the equation for conduction heat transfer, which is given by K. Now A, what is A? The area of heat transfer. So in this case, what will be the area? Area will be this breadth of this welded bond multiplied by length in the direction of this slide, into the slide or out of the slide. So this A here represents B into L. This area through which heat is transferred is given by breadth of this bond multiplied by length of this bond, welded bond. So into dt by dx, where dt is actually the temperature difference, which is this one, TB base temperature minus TF fluid temperature. So here the thermal resistance due to this pipe material is negligible or neglected, so that's why the temperature difference, this temperature difference is actually TB minus TF. So that is the heat transfer equation through this welded bond only by conduction, and we can write it in terms of per unit length. So that will be K into per unit length means L is equal to 1, so K into B over dx into dt, temperature difference. Right, so here we can define this term as bond conductance. Kb over dx is the bond conductance Cb, right, and 1 over Cb will be the thermal resistance, or dx over Kb. So this is actually Kb over dx is the bond conductance, where dx is the this thickness of this bond from this point till this point. That is the total or average, because this thickness is not constant over this whole breadth. So that is the average kind of thickness of this bond in this direction, in the direction of heat transfer, which is this one. That is the direction of heat transfer from TB to TF. So that is represented by in this book, this dx, or the thickness of this bond is represented by gamma. So that is the heat transfer for the whole length, TB minus TF, divided by this bond conductance. But for unit length, L is not mentioned in the book, so it is small q. Actually length is also there. Right. So and this dx is actually the bond thickness, which is represented by gamma. So cb is equal to kbb over gamma. So I have explained it in detail. What is cb? Bond conductance, right? Now the next term is the heat transfer resistance to this fluid, the convective heat transfer of this fluid which is flowing through this pipe, and that is given by HFI, the heat transfer coefficient between the fluid and the tube wall, between this fluid and this tube wall. That heat transfer coefficient is given by HFI. So in other words, we can write the same equation like this one. This was for the heat transfer equation for this welded bond. Similarly, we can write the heat transfer equation, the same QU is now from this pipe, inner edge of this pipe to this fluid, the heat transfer is by convection. So the equation will be HFI from Newton's law of cooling multiplied by area into TB minus TF. We are assuming the same temperature difference from TB to TF, but now this heat transfer is by convection. And what is this A? This A represents the heat transfer area. So for this portion, for this fluid, convection heat transfer to this fluid is through this whole area. What is this area? Pi d L. This is the pi d into L is the same length. So this area is actually given by pi d I inner diameter into length L, the length of this tube or the length of absorber sheet. It is the same L length. So for per unit length, this heat transfer is small QU is equal to HFI into pi di into this delta T, TB minus TF, delta T, which is TB minus TF. So in terms of heat transfer resistance, that will be 1 over HF into pi di into L, but L is assumed 1. So that is the second heat transfer equation, that the second heat transfer resistance. So this heat which was absorbed here, this is further transferred to fluid, and between this fluid and this absorber sheet or this portion of the absorber, these are the two extra heat transfer resistances. So now we have two equations. Now this is QU from base to fluid, and this was QU from the net heat transfer, the net heat absorbed on the surface of the absorber plate in terms of this TB minus TA ambient temperature. The same heat is now transferred to the fluid. Okay. So here is the heat transfer or the net heat gain of the absorber sheet over this tube, and second is the heat transfer from this TB to this TF. So now we have these two equations, and now we want to somehow get rid of this unknown base temperature. This base temperature is some unknown temperature. So, and we want to represent our main energy balance in terms of fluid temperature. So here we will do some more mathematical manipulations so that we can get rid of this unknown base temperature. So for this, what we do here is that we write this equation 6 and 7 in terms of per unit length, because this length L is actually common in every case. So we can write this equation in terms of length L, and also from 7 we will write this equation in terms of TB. So this TB is now will be shifted here in this equation 6. So So we will write this equation 7 in terms of TB for a unit length of the of this absorber or of this collector, and then put this value of TB here in this equation 6. So from 7, the heat transfer equation in terms of TB, so TB is equal to this whole term is multiplied by this Q. L is assumed 1 in both cases. L is assumed 1, so there is no L, so small q into this plus this fluid temperature is shifted to the other side. So that is the equation of TB from equation 7. So we will put this TB here in equation 6. So that now we will have equation 6, which represents the net heat gain of the solar collector, but only in terms of fluid temperature. There will be no TB. Right. So now put it in equation 6. So here is the equation 6, in which this D plus F into W minus D is written here separately, and here S minus UL into TB is replaced with this term that is shown here, minus dA. Right. So now this is the equation which we shall now simplify to another correlation which is easy to interpret. So now we shall be there are a number of mathematical steps which will now reduce this equation to a very simple form. Right. So now in this equation, only the fluid temperature is there, okay. And we want the purpose of all these derivations was to convert this general equation S minus U into TP minus TA to such equation where no TP is there. So now we will have an equation which does not involve this plate temperature. So it involves only fluid temperature. So now there are a number of steps from this point onwards, which we shall now discuss in next week's class. Right. So I have to end here for this week, and after sessional exam we will start from here onwards.